All right, continuing on section 4.3, we're talking about logs, and we're talking about how to calculate logs and how to graph logs. All about logs, 4.3. So I'm on number 5, and I want to talk to you about using the graphing tools. So the last problem, if you were with me, we talked about how to derive our own graph and steer our own ship, find our own points and plot and have kind of control on our paper to how we find that graph. Well, if it asks you to do it on the computer with a graphing tool, you will not get to steer your own ship. You will have to use these tools that are given, which I like it as well. I like both. I like for you to see both methods. But on this, for this example, it asks you to graph this log graph, and then it has a shifting rule on it. So we're going to use our old shifting rules we've seen throughout the course. But again, like I said, it will not let you drive your own ship and draw your graph over here. It just says graph this, and so you have to click on the graphing tool. So there's some sort of little graph box there. So you click on that, and then it brings up a graph, which also has frustrated a few of my students because it doesn't kind of give you a heads up that you can't position the graph where you want it. So if you've been paying attention, you probably know this graph is supposed to be moved up 6 places. 4, 5, 6. Normally, the typical pivotal point is, log graphs go this way. My bad. The typical graph goes to the point 1, 0 in standard form. So if you pay attention, you know this is supposed to be moved up or shifted up. That's a vertical shift 6 places. So the graph's going to be moved up and then look sort of like that. So maybe you know that, and maybe you tried already. We're already a little frustrated with this. You tried to put it where you wanted it, the graph where you knew it should be with the shifting rules, but it would not let you. So as soon as you click on this graphing tool, wherever you click, say you click here, you click wherever you want, it's going to draw it in standard form. So that's just what it does. It will not let you draw it where you want it using this tool. So it graphs it in standard form, and you have to tell it, also by the way, that you want to pick up the log tool. There will be a parabola, a line, and then the log tool in this box of figures to choose from. So you do need to know what figure this is. So you do need to know it is the log shape, which sort of looks like that shape. It normally goes through 1, 0. All right, so you click on that, and then again, like I said, it just draws it in the standard form for you. Then it pulls up these boxes for you to tell it where to shift it. So now, just to remind you, just to review, vertical stretch is when we have a multiplier in front of it. So if there would have been a 6 or a half, remember how multipliers affect the steepness of the curve? So we don't see anything going on here. It's just a regular 1. So don't bother this. And we just really haven't used the horizontal stretch feature. So really, you can look at a graph and think of it as stretching or shrinking it vertically or horizontally. And when we first introduced this in chapter, let's see, that was chapter 2. Maybe, and it showed up more in chapter 3, but you could use either way of thinking. So we did not necessarily see the horizontal stretch as a way of explaining the steepness of the curve. We looked at it from the vertical. So that box, just ignore it for our purposes. We will not be using that. But anyway, vertical stretch if there's a multiplier in front of the function. We have definitely used the shifting rules. So we have a vertical shift, which I've already kind of said on this one. That's a vertical shift when you have a standalone number added or subtracted. So you'll want to type in or move the little cursor over positive 6 places to tell it to shift it up 6 places. Horizontal shift is when it's grouped with the X, if it's included in the action of the X. So it's going to shift it left, right, horizontally if it's on X only. So in a parenthesis or in the denominator with it, under a radical, there were ways that we talked about that it was a horizontal shift grouped with the X. This is definitely a vertical shift. So we type that in. All right, what about these reflections? Reflections is when we turn the graph, either flip it across the y-axis or flip it across the x-axis. Those are reflections. Most of our work was across the x-axis, sort of flipping the graph upside down. When you have a negative in front of the function, like the parabola, we did that a lot in chapter 3, a negative would flip it upside down. That was an x reflection, or reflecting across that x-axis. So we're not doing that here. There's no negative. And then the y-axis, like I said, we haven't done that as much, but it flips it left-right when the negative is only on the x term. So nothing else is happening here. We just type in a 6 for the vertical shift, hit enter, and boom. That's all we need to do there. We don't actually drive it or graph it ourselves. All right, sorry for the long explanation, but maybe that'll help for future ones as well and review. All right, next question is talking about the expansion of logs, how that you can write this in expanded log form. And the log, I'm going to give a long explanation again, I think. The log rules are just like the exponent rules because, like I mentioned earlier, they're very closely related. They're sort of like sister operations. They're inverse operations. So they have the same rules, but just sort of show up differently in the way we write them, solving for a different piece. But when we do the log of base 4, let me see if I can speed that up. Log of base 4, we expand out each piece of this, the 5, the y, and the z. So we write log base 4 of 5. Then, because there's an understood times between the 5 and the y, times goes with plus in our log and exponent rules. Then we write log base 4 again. We write log base 4 every time, drag that along. Then we write the y, again because multiply meant to add those logs. And divide means subtract in the log rules. So we write log base 4 again of z. And that's all we're looking for there, is just showing that we understand that times means plus and divide means subtract. All right, number 7 maybe. This one is about converting, so back to that again. So to convert out of exponent form, that means log base 5 of the argument 3125, what we're trying to get, equals the exponent 5. All right, then back to graphing. These two are multiple choice, so you won't have to do what I had above. You can practice at graphing it on your own paper and then see which one it looks like. Or you might just know the standard form of a log with a base greater than 1. I haven't mentioned that yet in this section. You might have seen it in the lecture, though, earlier. But whenever it's greater than 1 base, it's an increasing function. Again, why do we call it an increasing function? It's if I lay my pen on that curve in any place along that curve, we consider that a positive slope. So that is an increasing function. And so the standard form, again, of a log function, it goes through the pivotal point of 1, 0. If it is a fraction base, like number 9, it still goes through the pivotal point of 1, 0, but it comes downhill. It's a decreasing function. So again, if you lay your pencil along that curve and any point along that curve, now it is going in a negative slope direction. So, it did say to label the vertical asymptote on these, and it kind of shows that in red. In standard form, again, these have no shiftings on them. There's no vertical or horizontal shift. So in standard form, there's a asymptote along the y-axis at x equals 0. And the pivotal point, again, is 1, 0. All right. Let me talk to you about the exponent rules before we move on and how we expand our logarithms. I knew I couldn't help but tell you more about that. When we had the log base 4 of 5y over z, why did I do it that way? Let me back up to our exponent rules. When we have, say, 3 to the second times 3 to the third, that makes 3 to the fifth. When you are multiplying with like bases, we add the exponent. So that's kind of an old rule we've seen maybe. Or if I do it with x's, say we have x to the second times x to the seventh, that equals x to the ninth. Again, because like bases, when we multiply, we add the exponents. So we've seen in our old exponent rules that multiply goes with add, 2 plus 7. So that's why whenever I saw the 5 times y, I said that's multiply, and that will expand to add. Log base 4 of 5 plus log base 4 of y. So again, multiply means add. Now what about this divide part? To remind you, if we had, let's do it with numbers first. Let's say we have 11 to the 5th power over 11 to the 3rd power. That equals 11 to the 2nd power. We subtract the exponents when it's division with like bases. So if we have x to the 9th over x to the 3rd, that equals x to the 6th. We subtract our exponents when we divide. If you have like bases, so it all is pivotal on the like base thing. So we write these with all this like base 4. So whenever I get to the divide part, I say minus, and I write it in like that. We're going to practice that some more and going back and forth between those two forms we'll see in this section. While I've got you on this, though, let's talk about the next rule. If we have a power raised to a power, like x squared to the 3rd, we multiply those exponents. A power to a power, called the power rule, we multiply. That's x to the 6th. So if I have x to the 5th raised to the 4th, I have x to the 20th. So if I'm doing log base 3 of 5 to the 2nd, let's say, I could expand that to this exponent is a multiplier. That a log is an exponent. The answer to the log is an exponent. So that's an exponent to an exponent. So that exponent comes down as a multiplier. It would be 2 times log base 3 of 5. So furthermore, on my example that I had before with the log, let's just come back up to this. And this one, and this will show up later in our homework, if this would have been squared, if you had all of this to a 2nd power, the 2 would wrap in front of that as a multiplier. Again, because exponents to exponents multiply. So I had a big 2 in front of all that answer. And then we could have distributed the 2 if needed. Another thing that comes up is log base 3 of square root of x, let's say. Expand that. Well, square root is the same thing as saying the 1/2 power. So we'll call that x to the 1/2 power. Again, square root, 1/2 power, same thing. So that is actually an exponent. So if you see a radical around a base, you do need to expand it with this rule and bring the 1/2 in front as a multiplier. Again, exponents are multipliers. All right, I think that will help us as we move forward with the rest of the problems.